Good afternoon, Huskies. It is time to do some more of the Mathematicus. All right, we are going to be working on some stuff today that's specifically designed about 10.2 arithmetic sequences and series. And to do some of these, what we're going to basically do, and again, I'm going to cut past all these ideas. Up until now in 10.1, we've been really focused on the ideas of what are called um, recursive formula questions. Ones where we were talking about a sequence that ended up having some kind of relationship to prior pieces that came before it. Now, what we're going to do in 10.2 and in 10.3 is we're going to take this idea of about sequences and we're going to break them down into some specific types. And the 10.2 section that you're going to be talking about today is going to be about arithmetic sequences. That's what this one is specifically about. Okay, now let's go down here to talk about what the title and directions basically say about arithmetic sequences. Okay, now first off, an arithmetic sequence is a sequence of numbers that is listed with a common difference. Now, let me give you an example of what I mean by a common difference, meaning that if I was to talk about, let's say, an easy one, like the even numbers that we've been doing up till now, 2, 4, 6, 8, 10, so forth, right? This is referred to as an arithmetic sequence because the difference that's going on in between each individual one is the same amount of common difference values going in each case. This case, it's positive 2. Okay, so every time this thing goes up by the same amount in that direction, it would be considered an arithmetic sequence. Now, arithmetic sequences don't have to just go up. They could also be a common difference that makes it go in a negative direction. So when we think about arithmetic sequences, we think about them being about positive and about subtraction, about pluses or minus. We could have, say, something that went from 5 down to 1, and then it went to negative 3, and then it went down to negative 7. And what you're doing right here is a common difference of negative 4 is what's going on here. Now, this would be still construed as an arithmetic sequence because arithmetic is based on either adding or subtracting. Just subtraction is the negation of addition. Okay. Now, if we're going to talk about arithmetic sequences, then we should also talk about arithmetic series. Now, remember that the word series means that we're going to talk about the word sum. So it's the list of numbers with a common difference, just like we've talked right here in arithmetic sequence, but the summation of that particular sequence, or with plus signs in between each one. So if we were talking about that even one, it'd be like 2 plus 4 plus 6 plus 8, dot, 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 down the line. This would be referred to as a series. Now, we're going to discuss each one of those particular ideas. One, how do we discuss an arithmetic sequence? And then how do we go about finding its actual series? Okay, now the first thing you're going to start out with here is they're going to give you one. It says, find the nth term of an arithmetic sequence, and we're going to consider this arithmetic sequence that's listed here. Well, first off, if you're ever given any sequence, you should check to see what kind it is. Now, this one does have a plus 4 combination that's going all the way up the cycle. This is your first common difference. And it looks like it's staying consistent all the way along. So I'd be like, oh, okay, this is arithmetic. That's what gives it away that it's an arithmetic type. Now, I'm going to go through a couple of these questions, and then we're going to run into a situation where we're going to have to actually do a little bit of work. Now, I'm going to erase this arithmetic part. It's going to get in my way. And I'm going to say, okay, I want to find the 5th term of the sequence, or better yet, a sub 5. Now, that wouldn't be too bad here because we've already got the first 4 terms. The 5th term would end up being this next one in line, which would be add 4 to it, or the number 19. Now, you're like, oh, dude, that's easy. That seems like a relatively easy plan. Now, it's going to get tougher. What if I wanted to find the 12th term, or a sub 12? Now, we know that that one is the 5th one, and then we'd be like, 6th one, 7th one, 8th one, 9th one, 10th one, 11th one, 12th one. Oh man, this is going to be a pain in the tuchus. 23, and then we go like 27, and then we got 31 and 35. You guys are checking my work, I hope. 39, and then 43, and then 47. Oh, I found a sub 12 down here on the end. Okay, now that was a little bit more cumbersome because I had to go so far out. Now, the problem is that what if you were looking for the arithmetic sequence way down here, somewhere down on the end, or better yet, the 112th term? Now, I know there's not very many people out there that are going to want to count this gosh darn thing all the way out to 112. So my question is there probably an easier way that I might be able to zip on down here to this particular spot and get that answer that's in that place? Well, let's kind of think about what you need to do to make sure that you can lock in this place and what it would be at that particular location. Well, the first thing that you would probably definitely need would be where to start. Okay, because if the starting point changed in any way, shape, or form, then the term that you're on would change too as well with it. So I'm going to say that one of those things that we're going to have to deal with is we're going to have a place to start. So if I wanted to say find the nth term of this particular sequence, or better yet, we're not going to do the nth term. We're going to do the 112th term. We would definitely need the first term to place to start from. And then from that first term, we would want to add on a certain amount of common differences. Now, when we did the fifth term, we added on once, 1 4, 2 4s, 3 4s, 4 4s. We added on 4 times. If we did the 12th term, we ended up adding on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. Now, there's something going on there. If I'm adding on 11 times for 12 and 4 times for 5, then I must be adding on the common difference n minus 1 times is what's going on right here. And then this right here absolutely does represent the formula. If I wanted a sub n, I would find the first term and I would add on to it the number of common differences that would be necessary to get to that particular term. Now let's try it with 112. If I wanted the 112th term, it would be 3 where the sequence started, and I would add on not 112, I'd add on 111 4s is what it ended up turning out to be. And if I did that particular term, let's see what we would end up getting. I'll go to my calculator, and calculator says, okay, I want 3. I'm going to clear this all out. I want 3, and I want to add on to that 111 times 4, because that's how many 4s we're going to add on to it, or 447. That's how much that answer would be way down here on the end. Now, let me say something about being able to zip to this particular location. That being able to zip concept, or this a sub n is equal to a sub 1 plus n minus 1 times d, is what's referred to as, instead of a recursive formula, because it doesn't have the a sub n minus 1, and it doesn't use the terms that come before it, so it's not recursive, this is what's called an explicit formula. Okay, this is an explicit formula to be able to zip, and that's what I like to think of it as. You can zip to a specific number wherever you want. If I wanted the 150,000th term, holy moly, yeah, I could go find it and I could zip right to it. I would not have to know the 149,999th term. That's not necessary. I can get right to that particular deal. Now, this explicit formula can be really super helpful in finding arithmetic sequences. And it really, be careful, this one only pertains to arithmetic sequences. Can't use it in any other circumstances, so it has to be a very specific type of sequence that you're going to use. Now it says, find the first 5 terms of the sequence. Okay, first 5 terms. First term's 2, because they told us what it was. Then they tell us the common difference is 4, so I'm just going to write them out. 6 and 10 and 14 and maybe 18, all right? That would be the first 5 terms. So understanding what a sub 1 means, meaning it's the start, and d means the common difference, that tells you what you're going to actually do. Now, there is a relationship between explicit formulas and formulas that are recursive. you can write a recursive formula that uses the previous term and adds something actually onto it. So for instance, if I said this one, first term is 3, and then I want the next term of the sequence where I'm at in the current, and I want to use the past, I would just add on 1.2. So it'd be like, oh, 4.2. And then I'd take that one and I'd add on to it to get the next one, oh, 5.4. And it turns out that this one happens to be a 6.6, and that's the first 4 terms. This one is a arithmetic sequence 2. So even though it was written as a recursive formula, you could actually write that recursive formula as an explicit formula as well. You could be like, oh, it's 3 times, or 3 plus, n minus 1 times the common difference of 1.2. And those two formulas right there that are listed are exactly the same. This is a recursive way to think about it, and this is an explicit way to think about it. Okay? Both of them are the same kind of ideas. Now, recursive ones don't tend to be written in arithmetic concepts this way because we usually use recursive ones for writing sequences that reoccur on previous ones and end up doing something to the sequence that's not necessarily just additive or subtractive. Okay, so it can be done though. Find the indicated term. Now, when they say these find the indicated terms deal, they're saying, hey, zip to that spot and tell me what you get. So what would you get if you wanted the 17th term of the sequence? Well, the 17th term of the sequence would have to have something to do with the beginning of the sequence, added to that beginning a certain number of additions of the common difference. Well, if I want the 17th term, I'd add on 17 minus 1, or 16 terms to it, and the common difference in this case is going down. So that sequence is going in a downward direction, or times -4. Now, if you plug this in your calculator, you get to punch it all out, you end up with getting -66. And that makes sense that the sequence started at -2 and it went downwards. So we're talking like -2s here at the beginning and then a whole bunch of stuff in between, and -66 showed up at the 17th term. Okay. Now the cool part is I didn't need to know any of this stuff in between. I was able to zip right to that particular answer. Now let's try it again. A sub 72, if I had a sequence that started at 23 and went down by went up by 0.5. Well, if I was just kind of thinking about that, up by 0.5, next one would be 23.5 and so forth down the line. What's the 72nd one? Ooh, I don't want to do that. Maybe I should go A sub 72 is 23 plus 71 additions of 0.5 is really what's going to go on. And if you plug that on, you get 58.5. Ooh, it sounds like it should be 58.5. I put 7 on my notes. Let's check this on my actual calculator. So 23, turn on. 23 added to 71 times 0.5. I like to put parentheses around 58.5. Sorry, that's what we should be getting, 58.5. Knew it should be ended in a 0.5. And that would be 72 terms down the actual sequence. Okay, now you get the idea. We're trying to find those arithmetic sequences. Now, here's what we're going to do is in the next part, we're going to write the formula for the general term or the explicit term. That's the same deal for it, for an arithmetic sequence, and then find that specific term. Now, what you're going to want to do is I'll show you on like the first one here, A sub 89 would be, the formula would be, it starts at the number 7 and you add on to it 88 amounts of the common difference. Now, you got to look at these to decide what the common difference is. Definitely starting at 7. Common difference is an addition of 3. You got to make sure it stays consistent enough so you can identify it. So that would be a 3 in that particular regard. And that answer would add up to 271, and that'd be the 89th term. Okay, seems pretty straightforward. Now, I want you to pause the video right here. I'm going to give it a couple of seconds of dead silence. You can check to try out these problems, and then you can come back and watch the presto bango of everything showing up. And poof, there's the answers that you're basically looking for. when it came to that. Now, I thought these first two, 6 and 7, really worked out pretty straightforward. It probably took a little bit of effort in number 8, realizing that it originally started out as a recursive formula that was written right there, but recognizing that the 2 is really the common difference that's going on right there, puts into light that you could plug it into the explicit formula relatively easy. Okay, now you got the idea of the a sub n is equal to a sub 1 plus n minus 1 times d. This gives you the explicit term in an arithmetic sequence. Now, this is one of 4 formulas that you're going to need to make sure that you have a good understanding for. And here comes the second one. Now, what if you wanted to take these terms that were going on here, but instead of just zipping to a specific one, you wanted to add them all up to that particular one? Well, that addition concept would no longer be a sequence. It would be a series. The sum would be a series kind of idea. Now, let's say we considered the sequence that's listed right here. Let's check this, make sure that it's arithmetic. It's going up by 4 all the way. And the series in this case would be the sums of all these individual numbers. Like that's 10 and that's 26 and this is, oh man, I can't even add that in my head. That must be 42. And if I added all those numbers together, I'd get the number 78. Now, the worst thing you'd possibly want to do, this was only 6 terms, and you wanted to add up, like, say, the one up above, which was the 28 terms, that could be a complete nightmare. Okay, so maybe there's got to be something a little bit easier or something that's a little bit more thoughtful. Well, one of the head people that came up with this idea of summing up arithmetic sequences was a mathematician by the name of Gauss. Okay, Nathaniel Gauss, famous French mathematician. And there is a story that goes behind with Gauss's concept of where he came up with this idea. Now, it's kind of an allegory kind of story. So I'm going to show it to you. It's even on the internet if you ever wanted to find it. So if you went to the internet and you searched Gauss, we're going to do it for you. Gauss. Carl Friedrich Gauss. Here he is right here. What a good looking guy this guy is. He looks like, a grandpa that would, hit you with a stick. All right, now it basically it says some stuff about what he's famous for and what his Gauss formula is or so forth. But what we want to know is about Gauss's arithmetic series story. There's a little story behind this. Now, I'm not making this up. It's on Google, so it must be real. Okay, so it says here, the story of Gauss and the National Council of Teachers. Here's what it is. It says right here, there's a little story about him. And it says, oh, that isn't the one I want. Hold on a second. It's Gauss's story. I think it's... The story's been flying around. Yeah, that isn't the one I found earlier. Man, hold on a second. I'll pause and I'll find it. Okay, I found the actual story, and it was at this Wazant Kiel. Okay, The Mathematical Journeys, Carl Gauss, and the Sum of His Arithmetic Series. So there was a famous story about the mathematical Carl Friedrich Gauss that goes something like this. When Gauss was 9, let's point that part out. When he was 9, people, he was sitting in his math class, and he was a genius even at a young age. Very similar to what Mr. G is. And as such an incredibly bored in his class and would otherwise goof off and get in trouble, one day his teacher wanted to punish him. Okay, now this has never happened to you because you're always good kids. Liars. So he told him that if he was so smart, why didn't he just go sit in the corner and add up all the integers from 1 to 100? Now, this teacher was smart. He was just like, all right, Gauss, you're pissing me off. I'm going to send you to the corner. So Gauss went to the corner and sat, but didn't pick up his pencil. The teacher confronted him and said, Carl, why are you not working? I suppose you figured it out already, haven't you? And Gauss responded with a presumptuous, yes, I have. The answer is 50,050. The teacher couldn't believe it, and he spent the next 10 minutes or so adding up the stuff by hand. Okay, poor guy had to add it up by hand, only to find out that Gauss was right. So here's the point. How did Gauss come up with the answer so fast? And why did he see that his teacher didn't? And the answer is really simple about the pattern recognition. And that's really what this all is about, explaining to you guys how to understand. There's patterns in everything that's going on. So the numbers, if we think about them from 1 to 100, look something like the following, right? Blah, 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 skip a bunch in between into 100. Now, it's true that adding them all up by hand could take you forever. But if you really needed to know how to add them up, it would make more sense if you just looked at the front number, the number 1, and the back number, the number 100, and you added those two together and you ended up with 101. Now that seems pretty reasonable, but the cool part is if you go one inside of that one and one inside of the other side, those two numbers add up to 101 too. And it ends up being that successively, as you count towards the center of the sequence, you end up adding up the same amount of those pairs. Now, if you did that all the way through to the middle, you'd recognize that the 50 and 51 add up to 101 too. And how many pairs of those would you really have? Well, you'd have 50 pairs of 101. And that would ultimately make a pretty simple multiplication problem where you would end up doing maybe 50 times 100. Because remember, Gauss didn't have a calculator. He just had, the corner to stare at. So he did 50 times 100, which is 5,000, and added on the extra 50 for the 5,050. Now, if you think about it, that whole concept that he just did there could be applied to any arithmetic sequence, because the idea of a 1 to 100 is just an arithmetic sequence with a common difference of 1. It would not matter if the common difference was different than that. So the concept boils down to that you would add together the beginning term and the last term, and then you would multiply it by the number of pairs that there would be, which would be half the amount of numbers that are in the sequence in the first place. Now, take a look at that. He was 9, people. He came up with this particular theorem, and he was 9. It took you till you were almost 19. You're behind the curve, peeps. Get on the gun. You can do this. So now let's see if we can figure out what we should write. So the formula for the sum of an arithmetic sequence would look something like the following. Well, first off, you would need to know that the summation deal is going to be a big S. This is the way they write this. And then they'd say, hey, we're going to sum up the number of terms that there are in the sequence. Well, those number of terms, like say 100, I want to sum up the first 100, or I want to sum up the first 50, would be about the number of pairs that there are first, which is the n number of terms in the sequence divided by 2. In Gauss's idea, that was 100 divided by 2, so it became 50. And then we should multiply it by the beginning term that he found, number 1, and add that to the last term of the sequence, and that's how you find the sum. Now, the thing to be thoughtful of here is that this sum formula has buried inside of it a sub n, which means that it has the other formula, the explicit formula, buried inside of it, or a sub n is equal to a sub 1 plus n minus 1 times d. Now, if I did this substitution and substitute it out, here's the basic formula of what you need to do, but you're going to have to use a sub n. You're going to have to find it anyways. If I did substitute it, I could write a secondary form, which would be s sub n would be n over 2 times a sub 1 plus a sub 1 from up here plus n minus 1 times d, all written out in one term. Now, you could write these two together as 2 a sub 1. Who cares? But you get the idea that one is substituted into the other one. So these two formulas work very closely hand in hand. All right, now what we're going to do is we're going to try to sum up the first 20 terms of that sequence that was listed up above. I think it was 3, 7. Yeah, it's the first 20. Now, I don't want to write the 20 terms out and write them out by hand and blah, blah, blah. I want to do this by Gauss's way. So I want the sum of the first 20 terms of the following sequence. Now, I know that this has got to be 20 divided by 2, but then I'm going to multiply it by where the sum starts at, 3. And then when I get to this spot, I have to pause. And I have to go, wait a second. I don't know what the 20th term is. So you have to do a secondary little piece of the problem. A sub 20 is a secondary part of the problem, so I can figure out what needs to go there. That would be 3 times 19, because there's going to be 19 additions of the common difference, which is times 4. And this turns out to be the number, I got to check my notes. This turns out to be the number 79, I think. I think that's what we're going to get right here. Let me check. Make sure I did my math right. Okay, it never hurts to check your math. Gauss always checked his. So 3 plus 19 times 4 would be the number 79. Now 79 goes in this particular location, and then it would be, okay, 79 plus 3, because that's how the pairing would be from beginning to end, and then I would multiply that number times 10, and I would get an answer of 820. Okay. Now, if you think that numbers in arithmetic sequences go up pretty fast, sums go up even faster because you keep summing up numbers that came up before that. So keep in mind that sums can be relatively big, or even better yet, relatively small numbers. Okay. Now, what I'm going to have you do is I'm going to have you try these 3 that are listed here using that summation notation, and we'll poof it and make an actual answer sheet here so you can see what you came up with. So here's your pause. And there you go. Poof! There's the answers again. I'm a mathematician, magician, baby. All right, here we go. So the first one I did was the 80 terms of the natural numbers. That's 1 through 80. And that would be ultimately starts at 1, ends at 80, and then ends up being 1 and 80. 80 divided by 2, ultimately 3240. Now, some things to be very careful of when you start talking about the way these things have been stated. This says the first 80 natural numbers. And those, I think it'd probably be better yet say that those are the first 80 counting numbers. If I was to say the first 80 integers greater than 0, be really careful when you start talking about the first 80. The 80th term, if I included 0 of integers that were greater than or equal to 0, would be 79. All right, so be very careful. Make sure that you understand the idea of inclusive or non-inclusive when it comes to a specific term. All right, saying, for instance, like here, find the sum of the first 50 positive even integers. You would not start this at 0 because 0 is not positive, nor is it negative, but I don't even think it's considered an even number. So be careful what you read in these statements so that you get the right sequence written out, and when you calculate the term that you're actually looking for, it should make more sense. So each one of those, I calculated the nth term that they were asking for, put it in the right spot in the summation, and then calculated the summation for how many terms they wanted into that idea. Now, you've probably seen this idea, the word sum, before, and you've probably seen it in this question where we've seen the summation or sigma before. Now, the cool thing about sigmas is this particular idea that when you make a sigma, it definitely tells you where you should start, which term you should start on, and which term you should end on. Now, this actually could be a really cool thing, because what if you didn't want to start at, like, say, in your sequence 2, 4, 6, 8, and so forth down the road, and you didn't want to start at 2, but you wanted to start at the 3rd term, and you wanted to sum them up from there to the 50th term. Okay, let's say whatever's going on there. That 25th term is what that one would be. Then you could actually do a sigma that says, hey, I don't want you to start at term number 1. I want you to start at term number 3, and I want you to sum up to term number 25. Now, that actually could be very helpful. It wouldn't change what goes into the sum formula up here. You wouldn't call it a sub 1. You would call it a sub 3, and you would work from the 3rd to the nth term that you were talking about. But you'd have to make sure you were counting the number of terms that are in between. Okay. Another cool part about the sigma concept is that we usually put a formula right here. The cool part in sigmas is this is the explicit formula. If you put the explicit formula in the spot right here, you will always get the correct summation. So for instance, if I was talking about an arithmetic one, if I always inserted on an arithmetic one right here, a sub n, whatever the a sub n formula was, and put this part of the formula in, which is a sub 1 plus n minus 1 times d in that location, I could get the explicit formula to give me the sum. Okay, so for instance, now you've got this one right here that's written. It wants the sum of the terms from 1 to 20, or the first 20 terms of possibly this explicit formula. Now, you don't want to do this by hand. This would be kind of a nightmare because you'd have to write every single one out. Welcome to the era of technology. Yes, indeed. We want to be able to make sure our technology works on this. Now, math, you're going to probably go back underneath your math key and be like, where can I find it, G? Where's it at? Well, it's under math, and I'm going to arrow to the bottom of the list, and above the log base is a summation button. And that summation button is listed right here. Okay, now it does blink with an alpha on it so that it's asking you for a specific letter. I'm going to call it X because that's easy, the easiest one to do. 1 to the number 20 of the explicit formula 2x plus 4. And it'll allow you to plug in an explicit formula in there and do the formula for you. And it'll tell you, oh, ching, that is 500. And that's how easy you can do these on sigmas. Now, if it, for some reason, your sigma is locked because maybe your teacher didn't get a chance to unlock it before you left, you can easily do this kind of stuff on Desmos too as well. So check it out. Maybe I might add an addition to the next one if you're struggling with it on how to do it on Desmos as well. But I'm going to do these a couple of these right here. So math, sigma or summation, and you can go from x equaling 0, and we're going to go all the way to 50. Now, if we think about this one very carefully, it is starting at 0 and going to 50. This would actually be 51 terms is what's being added because you're inclusive of 0. So be thoughtful on that. And then the explicit formula would be negative 3x plus 2 is what we came up with for our explicit formula in that one. And the answer would be negative 3750. How cool is that? It will add them up for you. Okay. Wonder what Gauss would say if he had such a device. He'd probably make you explode. Okay. All right. Now, what you guys want to do from here is you want to do your Math Excel for 10.2. And then you might want to check out, too, in some of those video links, Miss Merzak, Mrs. M, she's also putting on 10.2 and 10.1 so far, homework or Math Excel hints. So you might want to watch some of those if you're interested in making sure you get a good score on Math Excel. Peace out, brothers and sisters. G out.